Okay, hello Lexi, welcome back to your TP2 homework recap. This is homework 2. This recap is off center, so I'm just going to center that real quick. So this homework was about contour lines, gradients of contour lines, and line integrals and parametrization. Just as a warning, I kind of struggle with saying the word parametrization sometimes, so there's going to be times where I'm just going to breeze past it and you're just going to ignore the fact that I butchered the word. Anyway, so contour lines, here it says I have notes here, so we're just actually going to look through those notes that I made last semester. So contour lines here are a way to show functions with a 2D input and 1D output. So it's essentially, here, this thing actually, it's a slice of a 3D graph. It's like if you have a mountain and you take a slice and then you looked at the slice from above, and then like the different lines on the slice showed like the elevation of the mountain in a way. Or the elevation, or it would be more like a mountainous terrain, and then you could see the elevation using the contour lines. That's what it is. So, for example, in this graph here, this function, it's f of xy is equal to xy. F of xy can essentially be written as z, and xy is like sort of the different contours, and z is the height of whatever contour you're doing. So, because once again, we're working in a 3D space. So if you take z to be a constant height, then that's the same as taking a slice through the entire function. And so in order to find contour lines, you just set this function to some constant. And then once you set it to a constant, you can do different things with it. You mess around with it. You can analyze the function then. Here, like y is equal to c naught over x. And you could see that it looks similar to this, just like with different c naughts. And you can then graph the contour lines. The gradient of a contour line is always perpendicular to the contour line. You can find the exact vector of the gradient, like by just taking the gradient and then, for example, in this one here, you just input. Like if you want to find the gradient at point 1, 2, you'd input 1 and 2, or well, in this case, y is 2, so you'd input that to y, and then x is 1, so you input that into x, and you'd find the vector b, the gradient. Okay. I guess, gradient is pointed in the direction of steepest descent. You all kind of know that stuff. You kind of know all of that stuff, is what I'm trying to say. To go back to here, don't forget full analysis when I said analyze a function. Don't forget to analyze most of it. I'm pretty sure this isn't even all the analysis that you could do. I'm just silly and forgot. But look at its shape, what shape the function makes. If it's like a sphere, a cylinder, or a circle, look at its radius, look at its origin, look at its domain or its range, look at what happens when c changes, look at all those things. Tangent lines sometimes also come up, actually. So yeah. And like a little tidbit is, this is a cylinder. If you see a function that looks like this, it's a cylinder. Well, okay, so this looks like a circle, but since it's in 3 dimensions, it's a cylinder. So usually they'd put it as something like x squared plus z squared is equal to c squared, where you're missing a y squared, and you're like, oh, well, then it has to be a cylinder along the y-axis. This would be a cylinder along the z-axis. And of course, it's like a circle. It's radius root c squared, which is c. And yeah, that's the gradient. You know what gradients are. Line integrals. So these are important. This is very important part. Line integral of the thingy thing of the vector function times the line element, dr, is equal to this. So basically we're taking r, finding the time derivative or the t derivative or whatever, and then that gives you like this, right? So you can rewrite it, because now essentially you're going to parameterize r. You're going to parameterize r in terms of one variable, because usually r is going to be like x, y, z or something. We want r of x, of t, of y, of t, of z, of t. So it's essentially just all dependent on the one variable, so you can easily integrate over just t. Obviously, it doesn't have to be t. T usually just denotes like passing of time, but it can be any variable. So you just get dr dt is equal to rt. So that means dr is equal to r dot times dt. Now you could just sub this into here to get this. And now we have our r, which is in terms of t, and differentiating, and we're integrating, with only respect to t. Here I've just said, quote unquote, similar to the work force equation thing, like work is the line integral of force. I say similar to because it's just the same thing. A line integral of a vector field is kind of just like how much how much your line agrees with the vector field in a way. There are better people to explain this, but you know what I'm talking about. You're me. Okay. So just examples of parametrization. Parametrization of a circle. It's going to look like this. R cos t, R sin t, where t is between... Now, I've just put like random things here. It's usually 0 and 2 pi. But if we have a look at one of the example questions over here, it's actually asking what happens when a mass is lifted from here all the way to here. So, and we have... This is our reference for 0 radians. So this wouldn't be 0 to 2 pi. This would actually be like 3 over 2 pi to 1 over 2 pi. Yeah. So that's why I've just kind of put like placeholders in here. And the parametrization of a line, it's pretty straightforward. Let's just focus on x of t for now. It's going to be the initial position plus t and then this stuff. And this basically works. And we're taking t from 0 to 1 simply because it works. And I'll show you how it works. If we're at 0, t equals 0, we're at the very start. So we put t equals 0 to here, this whole term disappears, and you're left with just your initial starting position. Exactly what we want. Now, when t is equal to 1, it's at the very end. So when we input t equals to 1, it's going to be x1 plus, so now this is 1, so it's just going to be plus x2 minus x1. The x1s cancel each other out, and you're left with just x2, which is your final position, and exactly what you want. So that's homework 2. Thank you for listening to me.